Hello guys, good evening. And in this video, I will be solving chapter 2, the law of conservation of energy practice problems. So in this video, I'll only be solving 3 practice problems since each each problem takes about 20 to 30 minutes to solve. So that will take a lot of time to do the same practice number of practice problems as the previous videos. So in this one, I'll only be solving 3 practice problems, and I handpicked each problem in order to show how the um, general concept in solving chapter 2, which is the law of conservation of energy, specifically solving steady state, steady flow thermodynamic systems. So let's start. Problem 1. Assume a 5 pound per second of liquid enter a steady state steady flow system with a pressure 1 of 100 psia, density 1 of 0.2 pound mass per cubic feet, a velocity 1 of 100 feet per second, an specific internal energy 1 of 800 BTU per pound mass, and leaves with a pressure of 20 psia, a density of 0.05 pound mass per cubic feet, a velocity of 500 feet per second, and a specific internal energy of 780 BTU per pound mass. During this passage, through this open-end system, each pound rejects 10 BTU of heat. Find work in horsepower. So, the first step in solving thermodynamics problem is you need to list down the givens. So, I'll divide my given into 2 parts, which is going to be state 1 and state 2. This is just for convenience in order for me to easily distinguish which values I am going to use. So, at state 1, the pressure is 100 psia, and then the density 1 is equivalent to 0.2 pound mass per cubic feet, and then the velocity 1 is equivalent to 100 feet per second, and then the specific internal energy is 800 BTU per pound mass. And at state 2, pressure 2 is equivalent to 20 psia. The density 2 is equivalent to 0.05 pound mass per cubic feet. The velocity 2 is equivalent to 500 feet per second. And then the specific internal energy 2 is 780 BTU per pound mass. And then it says here, during the passage, this open-end system rejects 100 BTU of heat. So our heat here is, since the keyword here is reject, so our heat is negative 10 BTU. And another given is our mass flow rate. Mass flow rate is 5 pound mass per second. Since this is law of conservation of energy, mass in is equivalent to mass out. Therefore, mass 1 is equivalent to mass 2. And so that's it. And then the next step that we would do is we need to draw our system in order for us to visualize what we are trying to solve. So since elevations are not given, so therefore the system looks like this. So I'm gonna make this system a little bit simple, since our main goal is not about how the system looks, but the values, the unknowns that we are trying to solve. So this is my thermodynamic system, and this is my inlet, and this here is my outlet, like that. And at the left side, I'll put here state 1, and at the right side, I'll put here state 2. And the energies present at the left side, this is my general equation. I have my potential energy 1, my kinetic energy 1, my internal energy 1, my flow energy 1, and my heat. Then at the right side, we have the potential energy 2, the kinetic energy 2, the internal energy 2, the flow work 2, and my work. So that's for inlet, that's for outlet, and mass here enters, mass 1 and mass 2 leaves. And since elevation is not given, so that means our change in potential energy is equivalent to 0. Since the formula for potential energy is mass, gravity, and height, we know mass is constant, we know gravity is constant, so the only variable that will change is our the elevations from both ends. So since elevation is not given, so we do assume that our elevation is equal, so therefore the change in potential energy is 0. So our general equation, general energy equation is potential energy 1 plus kinetic energy 1 plus internal energy 1 plus flow work 1 or flow energy 1 and plus heat is equivalent to potential energy 2 plus kinetic energy 2 plus internal energy 2 plus flow work 2 and plus our mechanical work. And our main goal is to find work. So therefore, we transpose the other variables here to the left side and or to the right side, and then we retain our work. So the general formula for work is equivalent to potential energy 1 minus potential energy 2 plus kinetic energy 1 minus kinetic energy 2 plus internal energy 1 minus internal energy 2 plus flow work 1 minus flow work 2 plus heat. So this is our general equation, or let me put this one as equation 1. And since the change in potential energy is 0, therefore P1 is equivalent to P2, therefore we can just cancel this one out. And then, simplifying our formula, work now becomes kinetic energy 1 minus kinetic energy 2 plus internal energy 1 minus internal energy 2 plus flow work 1 minus flow work 2 plus our heat. So these are the unknowns. These are the variables that we are going to work with. So let's start with our kinetic energy 1. So kinetic energy 1. The formula for kinetic energy is 1/2 mass 1 velocity 1 squared. So substituting the values, we already have a value for mass and velocity. So 1/2 multiplied by our mass is 5 pound mass per second, and then multiplied by our velocity, which is 100 feet per second to the power of 2. And then simplifying this equation, we will get, let me just put it here, equals here, so 1/2, and then 5 pound mass per second, and then multiplied by 100 to the power of 2 is 10,000. So 10,000 feet squared, raise feet to raise the unit feet to the power of 2 and the unit second to the power of 2. And just like that, we have our equation. And then we need to create a unit of energy, or arrive at a unit of energy. So in order to do so, since we are doing it in the English system, we must use not energy, but not only energy, but we need first to arrive at the unit of force, and then another unit for distance. So simplifying this one, so let me just rewrite what I wrote here. 1/2 then multiplied by 5 pound mass per second, and then multiplied by 10,000 feet squared per second squared. So what we want is we need to create a unit of force. In order to create a unit of force, we need slug. In English system, we need slug feet per second squared. We already have a unit for foot, a unit of distance. We need to convert pound mass into slug, so we need to multiply this one by slug. So 1 slug is equivalent to 32.174 pound mass. So canceling pound mass, we have slug feet. We can use slug feet per second squared. So we have another feet here. So slug feet per second squared times foot all over seconds. So we can now convert this one into a unit of force, a unit of distance all over a unit of time. So simplifying and multiplying all of this, slug feet per second squared, so let me just put it as 5 pound mass times 10,000 times 10,000 all over 2 times 32.174. The resulting value is 777.025, and then the unit would be slug feet per second squared. That would be pound force times foot, or foot pound force per second. And foot pound force per second is equivalent to horsepower. You can convert foot pound force per second to horsepower by using the conversion. 1 horsepower is equivalent to 550 foot pound force per second. So we already have 777, so converting this one to horsepower, 777.025 foot pound force per second, and then 1 horsepower is 550 foot pound force per second. Cancel foot pound force per second, and our remaining unit would now be kinetic energy is equivalent to 777.025 divided by 550. It is 1.4128. 1.4128 horsepower. So our kinetic energy 1 is 1.4128 horsepower. And next thing that we would like to solve is our kinetic energy 2. Kinetic energy 2, the formula is still the same, 1/2 mass times velocity squared, but the velocity is we'll be using velocity 2. So 1/2, and our mass is still 5 pound mass per second because this is a steady state, steady flow thermodynamic system. And then our velocity 2 is also given, so velocity 2 is 500 feet per second. We raise this one to the power of 2, and simplifying, 1/2 times 5 pound mass per second multiplied by 500 to the power of 2. 500 to the power of 2 is 250,000. So this would be 250,000 feet squared per second squared. And since we will still be converting pound mass to slug, so I'm just gonna multiply here 1 slug all over 32.174 pound mass. So we can now cancel pound mass, and we can create a unit of force, a unit of distance all over a unit of time. So that means slug feet per second squared, that is pound force, and foot pound force per second, that would be, we can convert that one to horsepower. So simplifying, we need to simplify this first. So we will have 5 times 250,000 divided by 2 times 32.174. We will have 19,425. 19,425.6232 foot pound force per second. And now we will be converting this value to horsepower. So multiplying it by the conversion of 1 horsepower all over 550 foot pound force per second, canceling foot pound force per second, we will now have a value of our kinetic energy 2 in horsepower. So our resulting is 19425.6232, and dividing this one by 550, so we will have a value of 35.3193 horsepower. Alright, that's for our kinetic energy 2. And then the next thing that we would like to solve, we need to solve, is our internal energy 1. So internal energy 1 is equivalent to mass times specific internal energy 1. Mass 1 times specific internal energy 1. We already have our mass 1 and the specific internal energy is already given. So we just need to substitute our values and do our conversion. So 5 pound mass per second multiplied by our internal energy 1 is 800 BTU per pound mass. So we can now cancel pound mass. So our remaining units would be BTU per second. So BTU, there's a conversion from BTU to foot-pound force. So in order for us to convert BTU to horsepower, we must first need to go to convert this one to foot-pound force, and then foot-pound force divided by second, then we can convert that to horsepower. So I'm just gonna multiply here 1 BTU. I'm gonna put it at the denominator. 1 BTU is equivalent to 778 foot-pound force. That is the conversion, and I can now cancel my BTU. So the remaining units is foot-pound force, or foot-pound force per second. Now I'm going to convert foot-pound force per second to horsepower, doing the same thing I did earlier. So I'll have 1 horsepower at the numerator, and I'm going to put here 550 foot-pound force per second. So I can now cancel foot-pound force per second. And my remaining unit would be HP, or horsepower. So my specific internal, my internal energy 1 would be 5 times 800 times 778 divided by 550. So I will have 5,658.1818 horsepower. So and then the next thing that I would solve is my specific internal energy 2. My internal energy 2 by using my specific internal energy 2. So I have my mass 2. Mass 2 is equivalent to mass 1. And then we also have our internal energy 2. Specific internal energy 2. So simplifying this one, our mass is 5 pound mass per second, and then multiplied by our specific internal energy 2, which is also given 780 BTU per pound mass. I can now cancel my pound mass. I'm left with BTU per second and converting BTU to foot-pound force. So 778 foot-pound force divided by 1 BTU. So I can now cancel my BTU. So my remaining units are foot-pound force per second. Now I'll be converting that one into horsepower. And 1 horsepower is equivalent to 550 foot-pound force per second. I can now cancel foot-pound force per second, just like that, and I'm left with my unit of work, which is horsepower. So simplifying, I have 5 times 780 divided by 550. So that would be 5 times 780 times 778, so that would be 5,516.7273 horsepower. So that is for my internal energy 2. So I'm left with only flow work 1 and flow work 2. So I'll be solving it at the back of this paper. Let me just turn this one around, just like that. Let me just solve it at another sheet of paper so that I'll be able to directly see the values that I've solved previously. So next thing that I would solve is the flow work 1. So solving for flow work 1, EF1 is equivalent to the formula. Flow work 1, the formula is pressure 1 times volume 1. Since pressure 1 is given but volume 1 is not given, in order to solve for volume 1, we have a value for mass and we also have a value for density. So we can now solve for volume 1 by using the formula for density. Density is equivalent to mass over volume. Therefore, volume 1 is equivalent to mass over volume. Then volume 1 would be mass all over density. Mass 1 all over density 1 is equivalent to, mass is 5 pound mass per second, and then our density is 0.2 pound mass per cubic feet. So we can now cancel our pound mass, and then division of fractions, so cubic feet will go to the numerator and second will be our denominator. So it will become a volume flow rate, which is cubic feet per second. So simplifying this one, we'll have volume 1 is equivalent to 5 pound mass divided by 0.2. We'll have 25 cubic feet per second. 25 cubic feet per second. And then we already have our pressure, so we just need to substitute our formulas. The values for our formula. So pressure 1 is given by 100 pound force per inches squared, or PSI. And then multiplied by our volume, which is 25 cubic feet per second. And since inches squared and cubic feet, they are not uniform, we need to convert either one of them. I'm going to convert my inches squared because we need a unit of foot. So 144 inches squared at the top and 1 feet squared or foot squared at the bottom. So I'll be cancelling my inches squared and cancelling feet squared, and I'll cancel 3 here. To the power of 3, so I'm left with the unit of foot-pound force per second. And then since foot-pound force per second, I need to convert that one into horsepower. So I'll be multiplying here 1 horsepower all over 550 foot-pound force per second. So I can now cancel my pound force here, my foot here, and the unit of time. So I'll be left with the with horsepower. So my flow work 1 is equivalent to, simplifying the given values that I have arrived. So 100 times 25 times 144 divided by 550, the value will be 654.5455 horsepower. So this is my flow work 1, and then I'll be going to solve my flow work 2. So EF2 is equivalent to pressure 2 volume 2, and I'll be solving for my volume 2 the same way on how I solved my volume 1. So volume 2 is equivalent to mass 2, since mass 2 is equivalent to mass 1, so I'll be using the same value, and I'll be dividing it by my density 2, since density 2 is also given. So mass 2 is 5 pound mass per second, and then my density 2 is 0.05 pound mass per cubic feet. Now I can cancel pound mass, so cubic feet will go on top. This will become 5 divided by 0.05. I'll have a volume flow rate of 100 cubic feet per second. And now I'm going to substitute that one to my formula for flow work 2. Flow work 2 is equivalent to my pressure is, the given pressure is 20 pound force per inches squared, and then multiplying this one by the volume that I have arrived, 100 cubic feet per second. And then the same thing that I did earlier, 144 inches squared here, and 1 foot squared at the bottom, or feet squared at the bottom. Cancelling inches squared, cancelling feet squared, I'm left with foot-pound force per second, the same thing earlier, and I'll be multiplying this one by 1 horsepower all over 550 foot-pound force per second. Now, I'll be cancelling the units, so pound force, foot per second, foot-pound force per second, I'm left with HP. So the flow work 2 is equivalent to 20 times 100 times 144 divided by 550. So my resulting value is 523.6364 HP. So I have already solved all the variables that I need. So the next thing I would do is substitute it to my equation 1, which is work is equivalent to kinetic energy 1 minus kinetic energy 2 plus internal energy 1 minus internal energy 2 plus flow work 1 minus flow work 2 plus heat. Actually, I forgot to convert my heat. My heat is still in BTU. So I need to convert heat into BTU. Into horsepower. So my heat is negative 10 BTU. And BTU actually this is BTU per pound mass, because it says on the question, it says that each pound rejects 10 BTU of heat, so that means it is 10 BTU per pound mass. So this is not my actual heat, but this is just my specific heat. So I'll be using a small letter Q, and I'll be multiplying this one by my mass, which is 5 pound mass per second. Cancel mass. I'll be dealing with BTU per second, converting BTU into foot pound force. So 778 foot pound force all over 1 BTU. And I'll be canceling BTU, and I'll be canceling BTU on the bottom. I'm gonna put Q here, B. So foot pound force per second, converting foot pound force per second to HP. So 1 horsepower all over 550 foot pound force per second. So canceling the unnecessary units, I'm left with HP. So my heat rejected, since this is negative, is equivalent to negative 10 times 5 times 778 divided by 550. So the heat rejected is negative 70.7273 HP. So now I'm going to solve for my work. Work is equivalent to substituting all the values of the variables here. So kinetic energy 1 is 1.4128 horsepower minus kinetic energy 2 is 35.3193 horsepower plus my internal energy 1, which is 5658.1818 horsepower minus my internal energy 2, which is 5516.7273 horsepower, and then plus my EF1, or I'm gonna put that here, plus my flow work 1, which is 654.5455 horsepower, and then deducting it by my flow work 2, 523.6364 horsepower, and adding it by my negative heat, negative 70.7273 horsepower. So simplifying, I'll now be able to solve for my work. So 1.4128 minus 35.3193 plus 5658.1818 minus 5516.7273 plus 654.5455, then minus 523.6364, and then minus 70.7273. So my resulting work is 167.7298 horsepower. So this is my value for work.